Hello everyone, welcome to this video. Today I just decided to talk about something which I feel like everyone who is into additive manufacturing and is upcoming in the mechanical design field, or if you're a mechanical design engineer or you're a mechanical engineer, I feel like this is something that you ought to know. Okay, so my target audience for this is those who are into additive manufacturing and those who can 3D model for mechanical parts. So for additive manufacturing, I'm talking about the 3D printing, which is the FDM and the SLA. Okay, so yeah, when I'm talking about design optimization, how to optimize your design. So when you hear the word optimize, we're talking about reduction and performance. So that's what I understand whenever I hear the word optimize. When as long as the design field is concerned, that's how I picture it. Optimize. When you talk about optimize, talking about reduction and performance. Okay. So I feel like this is a very important information that I should share with everyone out there, especially those who follow me on LinkedIn, because I know that most of them are still coming up. But I know that when you do 3D modeling, you most likely want to own a 3D printer so that you can prototype and look at what the results are. So this is a very essential skill that you should know how to do using SolidWorks. I'm using SolidWorks for this. I think you can do this with other CAD software, but we all love SolidWorks, right? It's a user friendly. It has a user friendly interface and it's quite very much easy to use. Okay, so I'll give you a scenario and tell you why this is important. So let's assume you are designing a model for a mechanical pet, which I have on my screen right here. So this is a model. This is a an assembly that I prepared for this tutorial. So I designed this basically for this tutorial. I don't know what you're gonna use this for, but I'm very sure that so many machines have such application. But this particular tutorial is I just designed it for this tutorial. It's a particular model, I mean, assembly, whatever. So let's assume that this is a part that you have been asked to 3D print, or you got the part and you want to 3D print this particular part. So before I dive into this, I'm going to give you a quick explanation of what I have on my screen. So this is an apparatus, and this apparatus holds a mass, and this is a mass. This is the mass that is applied on this apparatus, and this mass exerts a force. The mass is a force. So the mass of this block is about um, um, 10 kilogram, or should I say 9 point something newtons. Okay, so this is the mass of this apparatus, and you see that the mass this apparatus this block is acting on this slide, acting on this. So you see that the block is acting, the force here is being applied on this body from this angle. So we have about three of these, and this slides around this. So this is a steel rod. This is a steel rod, is chromed, and also we have this as well. So I use PETs to 3D print, and PET is PET filaments, ABS filament, all these filaments that we use for mechanical parts, especially outdoor application. Is quite a little bit expensive. I would say it's a little expensive. But if you are into 3D printing, you would know that the major input is the filaments. Everything else comes secondary, which is the cost of electricity bill, that's the electricity bill and the time. But the major input is the filament, because without your filament, you can't print, right? So that's the major thing. And the same thing goes for the SLA printers. SLA printers use resin to print. It uses resin to print. So you're also buying that, right? So as you can see from this my model, let's just say I am designing this for maybe a project and I look at this. I just feel like, okay, this is functional, right? This is functional, this is going to function. But this has a lot of area, it has a lot of mass, and it does a very simple thing. It holds this block, it holds this block in place, okay, and as well it's light. So when we talk about optimization, I want to optimize this model. I want this model to be optimized. What I mean optimize, I want to remove as much mass from this model. But in doing that, I also want to keep I also want to retain its performance. I want it to still perform as well as it is doing right now. So that's the goal. The goal of this optimization is I want to keep the part performing as well as it is doing without being optimized. And when it's optimized, I want it to perform the same way. Okay. So you see, by doing that, by removing the mess, because when you're 3D printing with FDM printers, you see that the more the mass, the more filament is going to cost you, and the more the time it's going to take for a print. And when we are dealing with FDM printers, we hate. I don't know. I'm going to speak from my own perspective. I really hate long print. I dislike long print a lot because when it starts failing from the foundation, just keep failing upward. So try to keep my print as minimal as possible, and the longest print I can run is an 18 hours print, and that's really long. But I hate any print that goes up to 24 hours. I try to split it. Try to split the time. So, but let's say this print should take about, let's say, probably this is a large print, so it should take about 18 hours. But I want to remove mass from this print and I want to make it still functional. So we're going to be optimizing this model, and that's what the tutorial is all about. You can use this in so many other applications, but I'm going to teach you how to optimize your print. Okay, so to start this, we are going to open this part in a new window, but you should actually understand what this part is doing, because understanding that is going to be really helpful for this tutorial. So now we have this part open, and to start our optimization, we have a series of processes we have to follow. So some people might just jump right into the into optimizing this design using SolidWorks simulation and a popular simulation study called topology study. So I think topology, optimization, and generative design all mean the same thing. So they all do one thing: optimize. So some people can just jump right into optimizing, but I don't do that. That's what makes me a mechanical engineer. What makes me a mechanical engineer is, first of all, I want to know how this model is going to deform, how it's going to strain, this kind of stress that is on it. So the first thing I want to do is to get more information about the stresses, the displacement, the strain that is going on this model. Well, when some load is being applied on it. So to get those information, I'm going to run a static simulation. So I go to my SolidWorks tab, I click on SolidWorks add-ins, and I click on simulation. So when you click on SolidWorks simulation, it's going to take some seconds to open up to make the simulation feature available. So now it's out. So when you see this, you just have to click this, and when you click this, you can now start your simulation. So yeah, so you click new study. When you click on new study, you're going to select the kind of study you want to do. So the first study, like I said, I'm going to do a static simulation to get information on the stress, the strain, and the displacement. Okay. So this is what I want to start with first of all. So I click on new study, and you can see right here we have static. So when you click on static, you say okay. Now you have started the static simulation. So the first thing you want to do is to add. First one to do is to add. You want to add your material. So after designing, I've formed the habit of after designing my model, I always add material immediately. So if you haven't done that, all you just have to do is to you right click on this and you apply your material on the model. So I'll be printing this with a PET filament. So I've chosen PET as a material for my model. So I haven't added that. So you add that. The next thing you have to do is to define your fixture. Your fixture is where your part is going to be fixed. Okay, so my part is going to be fixed here and here. If you can recall from the model, from the assembly or the apparatus which I showed earlier, you see that this is where the part is fixed. The part is fixed right here, and also slides. So we're gonna have some kind of like a hinged fixture. So you go here, you right click on this, and you write fixed hinge. You click on fixed hinge. So you show SolidWorks shows a little animation on what you're doing. So you select. I'm just gonna select this and select this as well. So after selecting that, you click OK. So now you have just told SolidWorks that okay, this model, this is where it's going to be fixed. And what kind of fixture does it have? Is a fixed hinge fixture. So the next thing you're going to do is to apply your load. So I'm going to apply a force on this model according to my apparatus setup. So I have some kind of like a force pointing downwards. So I'm selecting this face, and this face. So these are the faces that the force are acting on. If you go back, you'll see that the force are acting downwards. Okay, not upwards, it's downwards. So I'm going to select 10 newtons for this. Select 10 newtons for this. Okay, this is 10 newtons, and I don't want it to be I want it to be a total force because we have a mass. The mass the mass is evenly distributed around the block. So I'm going to make it a total. It has to be I want it to be a total force coming downward on this part. So you select total, not because default by default is goes to per item. So it's important you select total because the output really differs. So when you do that, you click OK. So after added your force, the next thing to do is to create your mesh. Create your mesh, and I like to leave this at default. But you should know that the more the quality of your mesh, the much more better the results are going to be. But the disadvantage is if your laptop doesn't have a good computation speed, the slower is going to run that study. So you can run a study at a default mesh for 27 minutes. But if you increase the mesh quality to 100%, that's fine. Increase it to fine. That same model can run for hours and hours. So for this tutorial, so that I don't get a very lengthy computation, I'm going to leave it for as default. So I click OK with the mesh. So it's just going to take a few seconds to generate the mesh. It's not up to minutes. So we're going to wait for that a little bit. Yeah. Okay. Our mesh has been generated. So after generating your mesh, just have to have a quick look at it. So yeah, our mesh has been generated. So the next thing to do is for this static simulation is to run the study. So when you run the study, you're gonna get those informations. You're gonna see the total displacement, the total stress, and everything. So that didn't take quite a lot of time. Yeah. So this is it. This shows you this shows you how your part is going to deform. So that's the purpose of this static simulation. It shows you how where your part is going to default, going to deform, how your part is going to deform. So if I were to improve this model, I would know places to improve it from. I would like to improve it, maybe add some kind of a new design for this and something like that, and improve this and improve that. But from what we know right now, we are able to see SolidWorks was able to show us the 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 deformation of these parts when so amount of load is applied on it. And you can look at the displacement as well, and you see that the red shows where you have the total displacement. So you can find more videos about static simulation. That's not what I'm talking about today, but you can find more videos about static simulation as well. You can animate this and see what it looks like. So this is what it looks like. This is how your part is gonna deform. But that's not this. I'm not here to talk about static simulation. What I just want to do is to get information, and the most when you're dealing with this, the most information you want to get about is the displacement. The displacement here is 1 millimeters. So what I want to do is I'm gonna write this down somewhere. I'm gonna write this down somewhere. 1 millimeters, 1 millimeters. So I'm gonna write this down somewhere, and this is gonna tell me a lot. Okay, what it's gonna tell me is this part has a total displacement of 1 millimeters normally, like without being optimized. So what I want to do is, after I optimize this part, I want to compare the results and see if I still have a functional. So if at the end of optimization I don't have something close to the range of 1 to 2 millimeters, then I know that my the optimization is bad, because maybe that part doesn't need to be optimized. Yeah, so I just need this result to know whether my optimization was a good thing or a bad thing. But if you're looking at just to save your 3D printing cost of filaments, then you don't really to worry about the mechanical structure of this model. But yeah, I just need this information so that I could check, I could compare later. So after doing this static simulation, your static simulation is done. You've gotten your information, your stress, strain, and displacement. The next thing to do is to run your topological study or topology study. So topology, generative design, optimization, they all mean the same thing. So the topology is just all about removing mass or and constraints and all. So I want to run the topology study. Okay. So you could just go ahead and start a new study and run that as well, define the mass, define everything. But I already did this. So I want to use everything I have done here. I want to take the data I have done here and use the information I have here to run another study. So what I have to do is just right click on this. Instead of starting a new study, I just right click on this and copy study. So when you copy study, you can now select the study you want to run. The study I want to run is the topology study. So I click OK. So when you do this, SolidWorks automatically imports the parameters that you chose in the last one. So already I have my material selected, I have my fixture which is hinged, I have my total mass which is 10 Newton, or total force 10 Newton. So you need to pay very much attention now to this, because this is the way it works, and this is the way this works. And if you don't get this, you won't understand this. You see, topology study generates an alternative look for your model based on goals and constraints. So that's how it works. So it kind of runs a static simulation on your model, and if the goal of your study is to remove or to reduce the mass, what it's going to do is going to create holes in your model. By creating holes, it removes those mass, but it doesn't remove those holes from the parts that are essential, or the locations that are essential. So when it runs your static simulation, what it does is it looks for parts that doesn't react, that are not necessary, that doesn't react to the load, or the way you don't have strain or stress or displacement, and it removes that part because it's not necessary. Okay, so it removes it. So defining your goals and your constraints are really important. Okay, so I'm just sure how to do that. So first of all, you go to your goals and constraint, you right click on it. When you right click on it, you see three things. You see the best stiffness to weight ratio, which is always the default. You want to minimize maximum displacement, or you want to minimize the mass. So I like to choose the default setting because that is my goal. My goal is I want to minimize the mass of this but still retain the stiffness of my model. So when you click on that, it opens this, and this is where you define how much mass you want to remove by percentage. So I want to reduce the mass of this by 50%, or yeah, I want to remove the mass of this by 50%, which is okay. Then you can also define, you can also select other things like the displacement constraint, and you can choose the displacement you want to, you want how much displacement you want this model to displace after being optimized. But you need that information from the static simulation to know the displacement you have already. So the frequencies constraint the stress, but this is all I want, the mass constraint. So after doing that, just click OK. So now you have told SolidWorks this is your goal for this study. Your goal for this study to to reduce the mass but still retain its stiffness. So the next thing I want to talk about, you should pay close attention to, is the manufacturing control. So we have so many things here. We have you have to define the region you want to preserve. Okay, if you want to optimize, but you don't want but you don't want the model to lose its general look. So you can add the regions you want to preserve. You can specify the thickness. You can specify the demo direction. Okay, this demo direction is mostly for those who are into casting, when I mean casting, I'm talking about the injection machine manufacturing. That's if you want to manufacture your parts, you want to use injection mold for that molding process, or casting, or whatever. So you don't want to end up with a model that can't be manufactured. So this demo direction is really important for you if you're looking into that area. Then the specify symmetric plane. This is just telling SolidWorks that whatever you want to optimize on this direction, I want it symmetrical to another dimension, to a direction. But you need to specify a plane that is going to be in the middle of the model so that it could, be able to make that symmetrical. But I'm gonna go through this one after the other for this model. So first of all, there's some parts I want to preserve in this model, and I want to preserve these parts because it's essential. I want to preserve these parts, so it's essential as well, and also I want to preserve the overall look of this model and preserve the overall look. That's the outer faces of this model. Yeah, so I have to click that. I have to click all this real quick. I don't know if there's a way you could do that faster, but yeah, manually is how I do it for now. So yeah, so I clicked. These are the parts. These are the places I want to reserve. I don't want. What I'm just trying to tell SolidWorks is, you can remove mess from this, but do not touch these areas. So that's what I'm just selecting areas that I don't want SolidWorks to touch. So you can choose the depth of the reserved area. So I'm going to go 5 millimeters. That's how much I want it to retain. Then I can go to geometry preview so that you could see what it looks like before it starts the study. So what it's doing right now is generating kind of like a preview. It takes a little bit of time depending on your laptop processing speed. So yeah, so this is what it looks like. This is how much it's going to reserve, and this is 5 millimeters. So with that being done, you just click OK. So after doing that, another manufacturing control I want to talk about is the demo direction. The demo direction is yeah, from this animation, I believe the animation is quite explanatory. Shows you the demo direction. I think you understand this. So you have to just choose the location. So I want to, if there should be slots, there should be slots here and here. So that's what I'm trying to tell SolidWorks using this feature. So you click OK. You can change if you don't want, if you want it to be at the middle, choose that. Want it to be one direction, you can click on this. You want it to be a stamp that's go all through, you choose this, but mid plane is quite okay for me. So I need to add one more manufacturing control, and which is the symmetry plane. So this, like I said, this is what tells SolidWorks that whatever optimization you are making on this side, please make it on this side. So I'm going to choose a plane, and I already have a plane specified, and this is the plane. So you see that this plane runs all the way to the middle. So my optimization, whatever is gonna be here, is gonna be symmetrical to the back side. So it's gonna be front and back. So after selecting that, you click OK, and you are done. This is all you need to know about this. It's a very very simple process. Once you're done with this, you can just go ahead and create your mesh. So you create your mesh file. So after mesh, then you can run. So you create a mesh. I'm gonna reset this. I'm gonna make this to be at the middle, which is so I don't want to have to do with a very very large computation out. So reset this to be at the middle and click OK. It's gonna take almost, I think, the same time it took to generate the other mesh for the static simulation. So just a little bit time and your mesh should be done. So we're gonna wait a little bit for this. Coffee break. Okay, everything seems to be running smooth. Solid mesh in progress. Yeah, so SolidWorks is done generating the mesh. So you can have a look at it. If you feel like the mesh area is so small, you can generate much more thinner area. But like I said, the more the quality of the mesh, the more computation hour you're gonna have or time you're gonna take. So after generated your mesh, now you can just go ahead and run the study. Yes, now when you run the study, then SolidWorks will start optimizing this design. So this takes time. This takes quite a lot of time. It takes time depending on your laptop. But for me, I think this is gonna take close to 45 minutes or even more. So I'm gonna pause this video and jump to when it's done. Okay, so you just have to as long as you don't get an error when you click on that to run this study, you can just go have a coffee break or something. So I'm gonna stop this video for a while. Yeah. So welcome back, guys. Our study is done. This is what our simulation should look like when it's done. Our study should look like when it's done. So you see, you have materials removed from here, here, and here, and some little bit of here. So looks like this. It's okay. Now, as you can see, it is the constraints that you selected. It's preserved the region you wanted it to preserve. It showed this, it gave a slot all the way, and it's symmetrical. Whatever it's here is also here as well. So using the constraint, you're able to do that and reduce the mass. So you could just go ahead. Most people will just go ahead and export this file as an STL file and have it 3D printed right away. And just go and have it 3D printed right away. Not, I'm not going to do that because um, not because of it's a rough it has a rough body, because when you export this file, it's gonna be exported as a smoothed mesh, and I'll show you how to export that. So you have to do is just to right click on this and export as a smoothed mesh. Then it's going to be exported as a mesh file, and which you can convert an STL file, import it to your slicer software and 3D print it. But I don't want to do that, because what I want to do is I don't want to just export this as an STL file and just print it directly from this. I want to be able to control, like having power over the look of my model. So what I want to do, I want to be able to control how big or how small I want this hole to be, maybe in the future or whatever. So instead of doing that, I'll go back to my model. I'll go back to my model and cut those holes manually. So as you can see, this is the sketch for this cut. I cut those holes manually myself. So when I cut that manually, and you might ask, how do I know where to cut? Well, it's simple. All you have to do is to overlay. Let me show you. So this is a configuration. The unsuppressed. This is the suppressed. This is unsuppressed. Okay. Now you have two configurations. One is the normal, and one is the optimized model. So you might ask me, how do I know places to cut? Well, it's just quite simple using a SolidWorks building tool. Just click here and you click on simulation display, and it tell it where you want to display. So what it does is it overlays your model on top of the original one. So with this, you can now go to this plane, and sketch, which I did show you. Where is the sketch? Okay. You can now go to this plane, and you can now build your sketch top of that plane, as you can see. Then you can now cut it. So I had two cuts here. I had this cut, and I had this cut as well. So that that's it. So I like doing it this way. I like cutting it this way because I can, okay, if I send this over to a manufacturer and he complains that, okay, some places are too small, and other things, I can just manually go and increase the fillet or whatever. So it gives me full control of how I want these slots or these holes to be. So you can check whether this part has been optimized by, as in the mass has been reduced significantly by doing this. Go to the defaults, go to the tools, go to the evaluate, and click on the mass property. It gives you the mass of this part when it hasn't been optimized. So the mass of this part is 365.55 grams. So you see that it's going to take you point 3 grams to print this part. It's going to take 0.3 to print this part. That's 0.2 grams of filament to print this part. So, well, I don't know if you can see me. The funny story, the the light went off, my electricity went off while the study was going on, but I hope you can see me. So yeah, the mass of this part when it wasn't optimized is 365 grams. So let's check the mass when it has been optimized. So yeah, go to tools, evaluate, and mass properties, and you can see 221. So see, you have optimized this part by reducing the mass. So the mass has been reduced significantly, and you probably saved a lot of money. Yeah, just want to save money. This not much, but when you're working with a bigger model, you see that it saves you money as well. The cost of filaments. So this is for this, and the big question you want to ask yourself now is, okay, this part has been optimized. Does it still function? Yeah, it does. So how we're going to do this is we are going to run a new study. We're going to run a new study on the optimized parts. So this part has been optimized. So the last study we did on the part that wasn't optimized, we got about one millimeters of displacement. So let's talk about this. Do the same study on this part. So we fix this. We're gonna use the same parameter so we can compare. So that was why it was important to write that out. So I've already showed you how to do this. Running a static simulation on this using the same data I used in the other one. Yeah. So the load, select this part, and this part, and we create mesh for this um, defaults. Okay. Yeah. So I will call this a success if we have a displacement within the first one was 1.0 millimeters. So if the displacement is between 1.0 to 1.8 or 1 point or 2, yeah, 2 is the maximum. So if displacement between 1 and 2, between 1 and 2, then I'll call this optimization the success because as you can see in the apparatus we have three of them, so the load are evenly distributed. So it's quite okay. So we're about to see that um, generating mesh, taking quite a bit of time. Okay, our mesh has been generated, and you can just go ahead and run the study. So study is gonna start running. You know, the static simulation takes lesser time to run compared to the topology study because topology study requires a lot of computational data, but this one doesn't require much, so it's not going to take time to run. So study is done. Now you see we jump right into the displacement, and we have about 1.7. So we have 1.7. The former one was 1.0, and the optimized version is 1.7. So we have a displacement between 1 and 2. And it's for me, if you look at it, if you feel like, okay, the displacement is too much, you want to reduce displacement, you can go ahead and add more material or whatever. But for me, I feel like I'm okay with this. I'm okay with the results. So I have 1.7, and my part's still gonna perform. Still gonna perform. Wow, understand? So when you have checked this out, you can also animate this as well if you want to animate this as well, and you see the way it reacts to displacements. So the red, like I said, shows the places where you have the most displacement. So with this done, you have I've covered everything you need to know about the topology study and how to do the topology study. So I'll give you a quick summary. So the first thing you want to do is to run a static simulation to know where your parts are going to fail, the points that experience the most stress, strain, and displacement. By knowing this, you're gonna know how to improve your parts if you want to. At those points that experiences stress or strains. So first of all, you start the simulation, get those information. You keep those information aside, write it down somewhere, and you run your topology study by giving it the constraints and the goals. Then you compare. Then when you cut it out, or you can just go directly to printing it, or you cut it manually. So when you cut it, you again run a static simulation on the optimized model. When you run the static simulation on the optimized model, then you compare your result of a static simulation with optimized model to the result of your simulation or static simulation with the model that wasn't optimized. If the value isn't much, let's say between a ratio of 1:2 or something, I don't know. I'm going to explain that, but if the result you get after comparing the two results are fine by you, then you have an optimized model. So one last thing I would like to show you is how you're gonna load this up on your on in SolidWorks. I want to load this up in SolidWorks. How you want to load this up in your assembly in your man, I've been talking. Sorry, I'm talking quite a lot. My mouth kind of aches. So I'm gonna show you how to go and load this work in your assembly. So you go back to your assemble. So you don't need to. Okay, it's kind of loading up. It's updating, taking quite a while. Anytime now. Okay, so you don't need to go on ahead and start deleting this one and re-importing it or resetting the components. All you just need to do is select the model you wanna edit and right click on this and load up your optimized model and click OK. And your optimized model is being automatically um, replaced with the other one. So you see, we have optimized this model, successfully optimized this model, and we still have it performing from our simulation. So this is it. This is it, guys. And I would like to see you practice on this. So the more you practice, the more you're gonna be better at it. So we have one more. I know you have your eyes on this one right now. Yeah, I have my eyes on it as well. So I would like to see you all optimize this part. I'm going to leave a link to this file in the description. So I'd like to see you optimize this block right here. I'm done. I'm going to load this up so you can see. So I want to see you optimize this block because you can see, as you can see, it has a lot of mass that you feel like okay, it has a lot of mass because the load is only acting here. So you have a lot of mass and you feel like okay, you want this model to be optimized. So you have the mass only acting here and here. So you feel like there's a lot of optimization that can go on this model. So I'd like to see you optimize this as a practice. I'll leave a link to the description below. So that is all. I hope you like this video. This is my very first video to my road to starting up a YouTube page. So this is my very first video, and if you like what I do, I hope you just click the like and subscribe button. It's gonna help me know that what I'm doing is needed. Okay, bye. Thank you for your time.